My first argument was based on the origin of the universe. And I argued first that the universe began to exist. And here he says, well, but look, there are different multiverse scenarios, various models of the universe. I talked about those in my opening speech and explained that the Borde Guth Vilenkin Theorem applies to those and shows a beginning of the universe. In 2003, Arvin Borde, Alan Guth, and Alexander Vilenkin were able to prove that any universe, which is on average in a state of cosmic expansion throughout its history, cannot be infinite in the past, but must have a past space-time boundary. What makes their proof so powerful is that it holds regardless of the physical description of the very early universe. Because we don't yet have a quantum theory of gravity, we are not able to provide a physical description of the first split second of the early universe. But the Borde Guth Vilenkin Theorem is independent of any such physical description of that moment. Their theorem implies that the quantum vacuum state of the early universe, which some popularizers have misleadingly and inaccurately characterized as nothing, cannot be eternal in the past, but must have had an absolute beginning. Even if our universe is just a tiny part of a so-called multiverse composed of many universes, their theorem requires that the multiverse itself must have a beginning. Now, of course, highly speculative scenarios like loop quantum gravity models, string models, even closed time-like curves have been proposed to try to avoid this absolute beginning. However, these models are fraught with problems, and the bottom line is that none of these theories, even if true, succeed in restoring an eternal past. At most, they just push the beginning back a step. And then he says, but Vilenkin says that you can avoid the Borde Guth Vilenkin theorem by positing a contraction prior to this one.
In response to the question, does your theorem prove that the universe must have had a beginning? Alex Vilenkin answers, no. But it proves that the expansion of the universe must have had a beginning. You can evade the theorem by postulating that the universe was contracting prior to some time.
Now, this is a statement from a letter of Vilenkin to Victor Stenger, which is very often quoted out of context by atheists. Let me read you the full context. Vilenkin says, you can evade the theorem by postulating that the universe was contracting prior to some time. This sounds as if there is nothing wrong with having a contraction prior to expansion. But the problem is that a contracting universe is highly unstable. Small perturbations would cause it to develop all sorts of messy singularities, so it would never make it to the expanding phase. So he says, if someone asks me whether or not the theorem I proved with Borde and Guth implies that the universe had a beginning, I would say that the short answer is yes. If you are willing to get into subtleties, then the answer is no, but. That is to say, you've got the problem with the messy singularities that prevent re-expansion. So in fact, the Borde Guth Vilenkin theorem does imply an absolute beginning of the universe. Dr. Millican says, but we need a quantum theory of gravity to describe the early universe. The Borde Guth Vilenkin theorem is independent of that. Vilenkin says, the remarkable thing about this theorem is its sweeping generality. We did not even assume that gravity is described by Einstein's equations. So if Einstein's gravity requires some modification, our conclusion will still hold. So it isn't affected by having a quantum gravity description. Here's Vilenkin's conclusion. It is said that an argument is what convinces reasonable men, and a proof is what it takes to convince even an unreasonable man. With the proof now in place, cosmologists can no longer hide behind the possibility of a past eternal universe. They have to face the problem of a cosmic beginning.
So, okay, we want to find out about the beginning of the universe, how it began, and we have these three properties. We have the composition of the universe, we have the geometry of the universe, and we have the inhomogeneity as well as the homogeneity of the universe, and understanding those three. Now, each of the three, the mechanisms to explain that, are they indeed consistent with at least this universe having a beginning?
Yeah, all three of these depend crucially on the idea that the universe started out incredibly small and has been expanding dramatically since then. And that's what results in the cooling, which allows these funny processes that create a net baryon number to happen in the early universe, but then clearly they turned off. In the present universe, the baryons just sit there and are stable. And that's true of the other properties as well. So, yeah, it certainly looks like the universe that we observe around us, the universe as we know it, definitely had a beginning. That doesn't mean that that beginning was necessarily the ultimate beginning of all of reality. There may have been some prehistory to what we're here calling the beginning, but the universe as we know it certainly began, we think, about 13.7 billion years ago.
And the inflation theory, which explains some of those properties so wondrously, would engender the possibility of there being other beginnings, but I think you and some others have shown that ultimately there had to be some original, the mother of all beginnings.
Yes, that's right. Those issues are still a little unclear. I wouldn't say that those things are shown beyond doubt, but with reasonable assumptions, one could show that even in the context of inflation, with many bubbles forming, there would still be somewhere an ultimate beginning.
A theorem which actually applies in this most general setting, where you don't have to, where you cannot assume basically any energy condition, is this theorem, kinematic incompleteness theorem. Actually, I should probably have said they are called singularity theorems, but maybe a better name would be incompleteness theorem, because the theorem doesn't really prove that there is a singularity somewhere, it just proves that you cannot continue your space-time beyond certain region. So this kinematic incompleteness theorem that I proved with Arvind Borde, Alan Guth several years ago, very loosely stated, it says the following, that a space-time that is on average expanding, that is the average Hubble rate, is positive, is past-geodesically incomplete. I will give a more accurate statement in a moment. But the important thing about this theorem is that it is a purely geometric theorem. It doesn't assume any dynamics. That is, it doesn't rely on Einstein's equations. You could have some other theory based on some other equations. It also doesn't assume any energy conditions. Actually, both Alan and I mentioned this theorem when we were here 10 years ago at Stephen's 60th birthday. And from that, you can actually figure out the average time it takes to publish a paper when you write it with Alan Guth. Okay, so a more precise statement of the theorem. So first of all, I should say that an expansion is not really a property of space-time. It is a property of a congruence of geodesics in that space-time. And we say that a space-time is expanding if it can be filled with an expanding congruence of comoving test particles, that is geodesics. So let these black lines represent these expanding congruence of geodesics. And I want to consider some other geodesic observer different from these test particles who is moving through these test particles. Now, I want to denote h, the Hubble expansion rate of the congruence, in the direction of motion of the observer. I'm not assuming that the space-time is isotropic, so the expansion rate may be different in different directions. So that's why I specify the direction. And then the theorem statement, now with these definitions, is very simple, is if the Hubble expansion rate average over this world line is positive, then the world line cannot be past geodesically complete, cannot be complete to the past. The physical reason for this conclusion, actually the proof of the theorem is very elementary, and the physical reason for this conclusion is easy to understand. If you follow the geodesic to the future, then the velocity of the observer is redshifted relative to these particles, and the observer moves slower and slower relative to the congruence. But if you follow it to the past, the observer moves faster and faster. And what you can prove is that in a finite proper time of the observer, this observer reaches the speed of light relative to the congruence, beyond which you cannot extend the geodesic. So this tells you that that's where you reach the boundary of your region of space-time, and this happens in a finite proper time of the observer, so the space-time is geodesically incomplete. Now, it is an interesting thing that even though these geodesics of the congruence could be of infinite length, maybe they go all the way to past infinity, any other geodesic must be finite to the, incomplete to the past. So this shows that the past, that this space-time region must have a past boundary, and you can actually show that this geodesic reaches the past boundary in a pretty short proper time. So the corollary is that inflating space-times must be past geodesically incomplete, because inflation certainly is associated with expansion of the universe. And if the universe, so if you have this point as an inflating region, all the space-time to the past must also be inflating. And that indicates that inflationary universe must have a beginning.
Alex, I'm sorry. Does H average have to be bounded from below by a positive number, or it really could approach zero as you follow?
No, H can be negative or positive. All we require is that H averaged over.
Yeah, what I'm asking is whether H average has to be bounded from below by a positive number, or it's okay for it to slowly approach zero as you go backwards. Is that still?
Well, if it slowly approaches zero, then the average will be zero, right? Okay, so now an interesting proposal to avoid this conclusion was made by these people, starting with Aguirre and Grattan. What they suggested is that even though for simplicity, talking about de Sitter space as a prototype of inflation, even though full de Sitter space cannot be filled by expanding congruence of geodesic, it has kind of the contracting and expanding parts, but half of de Sitter space can be. And so what they said, okay, what if the arrow of time is reversed in a half of de Sitter space? So you can do it this way with a null boundary between the two parts, or you can do it this way with a space-like boundary. And then you would have bubbles nucleating, kind of expanding in the upward direction in the upper half, and in the lower half you also can have inflation with bubbles kind of going upside down. Okay, this avoids, of course, the conclusion of the theorem, but here you have to impose some boundary condition at the surface where the arrow of time is reversed. And for me, this amounts pretty much to a beginning. So I think I'm done with my list of things here with eternal inflation. So I think the conclusion is that that inflationary universe, even though it is eternal to the future, should have some sort of a beginning in the past.